this is the double modular redundancy system, and we're team number 8. My name is Alejandro Urcullo. That's Lou, that's UD, that's UA, and that's Jen. And our project is basically a system designed to protect signals in low Earth orbital satellites. Originally, there is a system called the triple modular redundancy, which uses 3 computers running at the same time, running the same programs, and it has a judge circuit at the end which combines all 3, and basically the best 2 out of 3, in case one breaks or one goes bad, it still checks the other 2, and the other 2 give out the proper output. We tried to make it smaller, to use fewer computers, save weight, save energy, by just using 2 computers and combining it all together.
Okay, I will introduce this part. As you can see, this part is a noise generator. The noise we're interested in is Gaussian noise. Why Gaussian noise? Because it is similar to the noise in the spaceship, in the space. So here we're design the circuit and to generate the Gaussian noise. Here you can see there's a potentiometer that can control our frequency of the noise. And we can also by use this potentiometer to control the amplitude for the noise we want. That's it.
For the 2 FPGA board, they have the same program in it. Also, the second one has a delay, so the noise influence of the 2 boards are the difference. You can see the programs are here. And this is the program. Due to the noise influence on the 2 boards are different, we will do mean values. Got the mean values after we got the output. So in this way, we can eliminate the high voltage noise for the space. And also in the FPGA board, we did a analog to digital converter and digital to analog converter. When we are doing ADC, itself has a sampling, so itself could eliminate some small noises. So when we are looking at when the noise is small, the distortion is very small.
This right here is the noise. This is what simulates as the noise. This is the adder. These 2 boards are the main part of the double modular redundancy system, and this is where the output goes, which has dividers and inverters and more adders, which will basically convert the output into something we want to look at. And then this shows the final output for the whole project. What we have here for the noise is we have the LM324N, which is basically a 1 IC that has a bunch of 741 op amps inside. We have 3 capacitors and a bunch of resistors with a potentiometer. And this creates the noise along with these 2 BJTs, transistors, by the output, as you can see here.
For these 2 FPGA boards, the loaded them the same program, which acts as double modular redundancy. The program includes 2 parts, AD and DC converting, and amplitude shift keying modulation and demodulation. Stage 1 is for open the system. Stage 2 is AD converting for analyze the signal. Stage 3 is PA converting. Stage 4 is amplitude shift keying modulation for achieve the purpose of long-distance communication. Stage 5 and 6 is ASK demodulate. Okay. In order to make the output seem different from the input sinusoid signal, we set the high bit of ADC part to 0. Now you can see the output of FPGA board. This is the output without noise inputs. Okay. Afterwards, we add the two outputs from FPGA board. Here you can see the amplitude is almost 2 times of original. Then we divide this output by 2. We use analog multiplier to build this divider. This is its output. You can see the signal is inversed. So we add an inverter at last. So at last, you can see the output waveform of the whole system.